Hello everyone. Our presentation, User-Controlled Offline Access for Anonymous Proof of Locations, is contributed by myself, Mamunur Akand, Sepideh Vijay, and Dr. Rihani Safavinaini. A proof of location, or POL, is a digital certificate issued by a trusted party called issuer, attesting the location of a user at a particular time. This certificate can be verified by a verifier and can be used in applications that need assurance about location of an entity. Applications of proof of locations are many, such as a reward system, where a store wants to offer discounts to frequent customers. Customers must be able to show evidence of their repeated visits in the past to the store. In supply chain management, the integrity of a product may be highly justified by the intermediate locations which a product travels, as it is transported from the manufacturer to the hands of the final customer. Proof of location can also be used by companies that want to audit the travel log of its employees. It can be used in police investigation, where a suspect may want to present a proof of location as their alibi. Proof of location systems can also be used in a larger security system, such as multi-factor authentication. A proof of location system must fulfill some requirements. The first one is unforgeability. Only a valid issuer should be able to issue a proof of location token to a valid user who is in the right location. The second requirement is non-transferability, that is, a proof issued to one user cannot be used by a second user. Many systems also require user anonymity, that is, users' identity should not be revealed to the proof of location issuer and the proof of location verifier. The last requirement is related to storage and presentation of proof of location tokens. Like most digital certificates and credentials, proof of location tokens are traditionally stored on user device. However, storing in a local wallet has the risk of the wallet being lost and POL, or proof of location tokens, becoming inaccessible. This asks for proof of location tokens to be stored in a secure, publicly accessible database and granting access to verifiers when needed. This approach is particularly attractive when a set of proof of location tokens must be presented to show the user's presence in a sequence of locations, such as a part of a workflow. However, the approach requires POL tokens to be robustly accessible to the verifiers with proper access at any time and from anywhere, and verify them even when the owner of the proof of location token is offline. Also, users should be able to manage access to stored proof of location tokens according to their own policies and requirements. And lastly, integrity of the stored data must be ensured. A distributed ledger or blockchain-based storage satisfies all these properties. We focus on three shortcomings of existing proof of location systems. Ideally, a user's interactions with the issuers and the verifiers must remain anonymous and unlinkable, and this must hold even when issuers and verifiers collude. None of the existing proof of location system guarantees this property. Secondly, there are mainly two ways we can model security for a system: using game-based approach or simulation-based approach providing composable security. Achieving composable security allows a system to be used as a building block of larger systems. This is significant for proof of location systems since these schemes may need to be composed with other protocols in a larger system, such as multi-factor authentication or identity management system. Existing proof of location systems, unfortunately, either provide game-based security model or informal arguments to prove security, and so lose their security guarantee in such scenarios. Lastly, publishing proof of location tokens on blockchain and central databases have been considered before. However, none of these systems consider user-controlled access to their proof of location tokens. And as such, we have three main contributions: construct a proof of location system that achieves full anonymity, that is defined by the inability of the POL issuer or the verifier to link a Paul token to a user. We use simulation-based security definition that guarantees sequential composability of Paul scheme that ensures that the proof of location scheme remains secure when protocol instances are composed sequentially and possibly on related inputs. Lastly, our construction allows the user to control access to proof of location tokens that is stored on blockchain. We give a proof of concept implementation of our proposed Paul system to show feasibility and practicality of the solution. The figure on the left shows our proposed Paul system model. There are 5 types of system components: users, issuers, verifiers, the blockchain, and the registration authority. The blockchain is used to store the issued proof of locations and thus providing offline accessibility. Figures on the right are the 4 protocols of our system that use cryptographic primitives such as commitment scheme, zero knowledge proof of knowledge, digital signature, and symmetric key encryption. A user U who has been registered to the system by the registration authority forms a pseudonym with the issuer, which she later uses to obtain a proof of location token or Paul token from the issuer. Once a Paul token is generated, the issuer also writes the Paul token in encrypted form on the blockchain. The decryption key as well as the index to search the Paul token on the blockchain is returned to the user. User is now able to issue a Paul access token to a verifier, which contains the corresponding decryption key and index to the proof of location token stored on the blockchain. Verifier, using this index, can search and read encrypted Paul tokens from blockchain, decrypts it, and verifies the proof of location token. We assume a public permission blockchain. Only issuers and registration authority can write to the blockchain, and all other parties can read. Our construction achieves full anonymity that is defined by the inability of the Paul issuer or the verifier to link multiple Paul credentials that were issued to a particular user. Being built on cryptographic blocks such as zero knowledge proof of knowledge and commitment scheme, the proposed scheme achieves anonymity against issuer by allowing the user to choose a different pseudonym in each protocol session with the issuer. Anonymity against the verifier is assured by making the proof of location tokens independent from each other, thus preventing the verifier from linking multiple Paul tokens to a single user. Paul token privacy is ensured by encrypting it before publishing on the blockchain. User control is achieved by allowing the user to control access to Paul tokens on the blockchain. And we also provide user-controlled linkability of Paul tokens by allowing the user to include a zero-knowledge proof of knowledge with the token and prove ownership of multiple Paul tokens. We give a proof of concept implementation of our proposed Paul system using the IDMX Java library for an off-the-shelf Android smartphone and a MacBook Pro. We use the library to implement the cryptographic components of the protocol, including commitment, zero-knowledge proof, and signature scheme. The implementation's aim is to determine the processing times for a user, issuer, registration authority, and verifier. As can be seen in the figure, the execution times are reasonable, with longest execution times being 200 to 185 milliseconds for proof of location generation in issuer and user respectively. Our implementation also examines the storage costs of the system. The size of the Paul token is less than 2 kilobytes, which is a reasonable amount considering the storage capacity of modern devices. We compared our results to the proof of location scheme implemented in a related work. The size of the proof of location token in their work is more than 3 kilobytes, which is bigger than ours. To summarize, we proposed a proof of location scheme that can be used as a building block in a wide range of security protocols. Our protocol achieves user anonymity with respect to both issuer and the verifier. For offline Paul accessibility, we designed Paul scheme in a way that user can control their own credentials while achieving all the security properties. Our implementation shows feasibility and practicality of the system. The future research direction is to use blockchain for storing location provenance information for providing a sequence of locations visited by a user. That is the end of the presentation. Thank you for listening.